Alright, vocab. So I'm going to cover all the vocab. It's going to be very long. If you know the process of looking up the vocab in the reading material or whatever, it'll be faster than this. Okay, so this is going to be a slow breakdown deal. So just so you know. So in other words, if you do this on your own, you will move much faster than I am going to move right now. Cool. Alright, so here we go. Nuclear stability, fission, and fusion, vocabulary. As you read the definitions, write the definitions or equations. In other words, break down each one of these. Most of them are definitions. I think all of them might be. You know, every now and then in physics, you'll have things that are really just best described with an equation. I don't think any of these are those. So, here we go. Nucleus. This is our first word. Excuse me. So, nucleus. It is a positively charged center of the atom, that contains protons and neutrons, and has almost all of the mass of the entire atom, but only a fraction of the volume, right? So, let's rephrase that. So, this is our nucleus, right? This is like the cloud, whatever around. In the nucleus is the center, right? What does the nucleus contain? Well, it contains almost the entirety of the mass. So that automatically tells us that so if this is my nucleus right here, it has protons in it, and it has neutrons. Protons and neutrons, because those are the things that have mass in an atom, right? Remember that orbiting an atom are the electrons, right? They don't really have mass, or it's negligible, we'll say. So the main mass in an atom is a proton or neutron. They are inside the nucleus, right? Bam, smashed together. So I'm not going to write it all out, but I will say it again. The positively charged center of an atom, which contains protons and neutrons, has almost all the mass of the entire atom, but only a fraction of the volume. In other words, it's super tiny compared to the whole volume. That's probably not drawn to scale, right? Alright, so let's move on to proton. So we just did this one. So let's go to proton. Proton, positive. That's easy to remember. So, a positively charged particle that is one of the two kinds of particles found in the nucleus. Well, we already talked about that. So protons and neutrons are the particles found in the nucleus. So it's a positively charged. So what do we take away from this? Protons are positive, and they're in the nucleus. Alright? Obviously, you need to write out a sentence. Alright, let's go to the next one. Neutrons. Electrically charged neutral particle that is one of two kinds of particles that compose an atomic nucleus. So, protons are positive. Neutrons, I know it's a habit to be like proton positive, neutron negative. Neutrons are not negative. Neutrons are neutral, right? Like a neutron, neutral. They're in the nucleus and they are neutral. No charge, right? No charge. You guys need to write a sentence. The sentence that I said or something similar to it. Okay, electrons. We talked about this already, right? So electrons are negatively charged subatomic particle that orbits the nucleus of an atom. So, is it in the nucleus? No. It's orbiting the nucleus. And they're negative. So let's break something down. If something gains electrons, it becomes positive or negative. We'll say more positive or more negative if it gains electrons. So if it gains electrons, hopefully you said this, it becomes more negative because it's gaining negatives, right? If it loses electrons, it'll kind of lean towards more positive, right? If it has an off balance. Because it's losing negatives, right? So think electrons, they're like debt. If you gain debt, you gain electrons, you're really losing money, right? Okay, so strong nuclear force. If you try to look this up, you probably can't find it because it really never specifically says. It's a vague definition, but it's just an attractive nuclear force. An attractive force in the nucleus. Bam. Just write that down. Don't worry if you can't find it. Ooh, I have not been checking off. Check, 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 check. So, strong nuclear force, let's write the definition as an attractive nuclear force. That's important when we talk about fusion and fission, right? Okay, radioactive. I know you guys have heard that term, radioactive, if you've learned anything about atomic bombs or you played Fallout series. You've seen radioactive, right? So, it's a term applied to an atom with a nucleus that is unstable. So the nucleus, the center of the atom, is unstable and spontaneously emits particles that become like nucleus of another element. So, and become the nucleus of another element. So, what does that mean? That means it's kind of like, let's say you're building something with clay, or you're building something with mud, and it's not solid, so things just keep falling off of it, and it becomes a completely different shape. Well, you have certain atoms that are really dense, really heavy, and they spontaneously sort of decay. And we know that each element is defined by its number of protons, right? So, for instance, hydrogen has, it's 1 because it has 1 proton, right? And I believe helium is 2 because it has 2 protons. So for instance, if helium were to decay and lose 1 proton, it would become hydrogen. Because remember, the definition of elements is just how many protons they have. And that defines, its characteristics and stuff. So when these things like plutonium and stuff, when they decay, they actually will become other elements, right? Okay, let's keep going. Isotope. A form of an element having a particular number of neutrons in the nuclei of its atoms. Different isotopes of a particular element have the same atomic number. Atomic number, remember, is just the number of protons, right? So remember that, atomic number of protons. That's pretty straightforward. So let me rewind a little bit. Different isotopes of a particular element will have the same atomic number because they'll be the same element, right? But they'll have a different atomic mass. Okay, let's break that down. So what defines an isotope? Something with a different amount of neutrons. That's all that is. So, for instance, let's do some random explanations. So let's say you're carrying around, and you normally always carry around 20 apples. Always carry around 20 apples. And that's your mass, you plus your apples, right? You being the amount of protons and the apples being the amount of neutrons. You can change the amount of apples you carry. And that's okay, because your identity doesn't change. You're still, Billy or Sarah or whatever with X number of apples. One day you have 10 apples. Another, version of you, maybe you'll have 5 apples. But you're still you, right? Now remember, when you gain or lose apples, your mass changes naturally, right? Because apples have mass. Think of the apples as the neutrons. So when you are carrying 5 apples, your mass is less. You'd be a different isotope than when you are carrying 10 apples, right? But you yourself, your atomic number, which remember is the number of protons, that's the atomic number, that doesn't change because that's you, that's your identity, right? So, to reiterate, an isotope is an atom with a different number of neutrons. Atoms, there's different isotopes of different atoms. Obviously, they have different masses because, as we said earlier, in an atom, protons and neutrons have mass. So if we add or take away neutrons, we're adding or taking away mass, right? Okay, so let's keep going. Transmutation. The conversion of an atomic nucleus at one element into an atomic nucleus of, That was not add, it was up. So the conversion of an atomic nucleus of one element into the atomic nucleus of another element through gain or loss of number of protons. Okay. So let's break this down. So transmutation. Trans means like change, mutation. So we talked about earlier, an element is defined by its number of protons. If it has one proton, I don't have to tell you what it is because you know it's hydrogen. If we add another proton to that, you know it's helium, right? Because that's what defines an element. If I have one proton and I have 10 neutrons, it's still hydrogen because it has one proton. If I have one proton and I have 100 neutrons, well, again, it's still hydrogen because it's not defined by its neutrons. It's defined by its protons, right? So when you think about that, just think about Legos. I mean, you can imagine all this stuff. So, you know, if you have hydrogen and you give it a proton, you have transformed hydrogen into helium. I mean, that's all you've done. That's how atoms are made in stars. Stars push together hydrogen. They take two number ones, which is just hydrogen, right? They smash them together, they fuse, and then they become a stinking number two. And that's how you have all these elements. That's the elements in your body are made from things that are essentially made in stars, right? So, transmutation, again, it's the conversion. You're taking an atom, atomic nucleus of one element, into the atomic nucleus of another element through gain or loss of protons. So you have an atom, you add protons to it, it changes the element, or you take away protons, it changes the element. You can add or take away, right? Cool. Good, good, good. Trans, change, right? That's easy. Okay, and then the main words of this unit. We got nuclear fission, nuclear fusion. One of them you'll remember, and the other one you'll be like, oh, I know what this is because I know what it's not, right? I can always remember fusion easier, and then when I hear fission, I'm just like, oh, it's the opposite of fusion. But you'll have your own, right? So, let's start with the harder one, even though they're not hard. Excuse me. Alright, so fission. Fission. The splitting of an atom, particularly at a heavy element such as uranium. Uranium is 235. Into two main parts accompanied by the release of much energy. Okay. So what does that mean? You have a really big atom. You break it. You split it. Remember, let's say it's made out of 100 protons. When you split it, you're going to have two atoms that are made out of what? Well, 50 and 50, right? Makes sense. What happens when you split it? What gets released? Energy! Energy. Lightning bolt. Lightning bolt. Lightning bolt. It's from a LARPing game. So, releases a ton of energy. This is a version of a bomb, a fission bomb, right? Bombs. And it releases a lot of energy. A lot, right? It's like crazy. So, there you go. This is how I believe nuclear reactors work. Right, release a lot of energy, they heat up water, water spins turbines, you get a lot of power, all that good stuff. Alright, so if fission is splitting and releasing energy, you can probably imagine what fusion is going to be, right? So let's go to this one. We just did fission. Fusion. The combining of a nucleus of light atoms, such as hydrogen, into heavier nuclei accompanied by the release of much energy. So, in other words, you take things that are light, like hydrogen. Yay, little hydrogen. So happy. You smash it together. You combine it. Remember, hydrogen's one, right? 1 plus 1 is 2. That turns it into helium. And guess what? What gets released when you do that? Whammo. Energy. Bam, bam, bam. Look at that lightning bolt. That is crazy intimidating, bro. You see that lightning bolt? It's like a flash lightning bolt. Bam. So, fusion. You fuse things together. Right? So, again, fission equals you break up. Fusion equals you get together. That's pretty simple, pretty straightforward, right? So, whatever one you can remember easier, remember that one, and then you know the other one's the opposite. If you guys got any questions about the vocab, please let me know. I will further explain it with anecdotes and random stories. Keep on rolling. You're doing good, guys.